So in this video I want to talk about the concept of vectors. Vectors are a new type of mathematical quantity that we're going to learn how to get comfortable with dealing with, and they're important because they show up a lot in physics. So the idea is there's different types of mathematical quantities. The first type is scalars, and these are the things that you're used to dealing with. They're just plain numbers. So these are quantities that are represented by a single number. Quantities, so a single number or a quantity represented by a single number. And in physics, these are quite common. So if I ask you how tall you are, you can give me your height in inches, and it's a single number. If I ask you how heavy you are, you can give me your weight in pounds, and it's a single number. All of those quantities are what we think of as scalar quantities. Vector quantities are characterized by two different values. So these are described by two numbers. And if we think about what those represent, often it's basically boils down to a magnitude and a direction. So the scalars, they're typically just thought of as just the magnitude. Vectors are a magnitude as well as a direction. And there are lots of things that show up in this context as well. So just again to highlight, scalar quantities would be things like a height or any length. So a height or some sort of distance, or the mass of something, how much you weigh. So these are examples of things that would be considered scalars. Vectors, on the other hand, because they involve both a magnitude and a direction, these are things like velocity. So not just how fast is something going, but what direction is it going as well. Acceleration. How fast is something speeding up, and in what direction is it speeding up? And a big one that shows up a lot in physics is force. And these aren't the only ones, but these are some examples of these different types of quantities. So again, this is magnitude only. And these all involve a magnitude and a direction. Okay, so again, we want to focus on vectors. You've already spent years working with scalars, just typical single number values. So, how do we represent a vector? Well, it turns out there's a bunch of ways. And we're going to kind of go through hopefully pretty much all of them, so you can kind of learn what to expect, cover all your bases of what you might encounter. A vector is kind of, you can think of it as basically like an arrow. So get that deleted here. Okay, so think of it like a little arrow where we have a starting point and an ending point on this arrow. If I label this point over here A and this point over here B, I can think of this as the initial point, the point where the vector started, and this point over here where it ends we call the terminal point, where it ends. And so you can see, looking at this thing, it has a length, that would be its magnitude, but it also has a direction. This one's kind of pointing up and to the right. But I could have drawn a different arrow pointing up and to the left, or down and to the left, or down and to the right, and it would have a different direction. So this has both a direction and a length or magnitude. Some of the notation that you will see when it comes to something like this is we may give this thing a name. You may have seen something like this before if you've taken any sort of geometry class. They would write sort of a ray, a line segment, but a directed line segment A, where they put a little arrow over the top of some sort. So you might represent this vector in that particular way. For us, we don't want to have to label the endpoints of our vector. Typically what we'll do is we will label it with just a single lowercase letter, and I'll put a little arrow over the top of it. So all of these represent the same thing. This whole thing is that vector. I could maybe call it the vector u. I could call it the vector AB with this little arrow over it. And if we want to think about the magnitude, one other notation that you'll see, this length, the magnitude of this thing, we can write it using the existing notation. We can write it either this way. You may see it written like this with sort of absolute value looking symbols around it, or you may see double lines. You may see it written like this. I think this is the notation that our book actually typically uses, is the double lines. Or if we are using the AB notation, equivalently, either single line or double lines, but something that looks like this. So again, this is going to be my preferred notation, along with, I usually do this, but you may see that written as well. All of these are just kind of the notations that I will be most likely to use, so just keep that in mind going forward. So just a quick note on notation, and there's going to be additional notations after this that we'll learn later on. In the textbook, and in most textbooks, the vector version of u would be written in bold. So basically, they would write it like, if that's how I normally write u, they would just make it a bold lowercase letter. But I can't really write a bold letter U in my handwriting, so that's why I'm just going to adopt a U with a little arrow over the top. But you may see other instructors, they may write a U with just like a line underneath it, or a U with a full arrow underneath it. All of these mean the same thing. And they're all because we can't write bold by hand very easily. My handwriting doesn't do bolds very well. So this, again, this will be the notation you'll see me using, but if you were taking another instructor, they may use one of these alternate notations over here on the right. Okay, so let's take a look at what these things, how these things work. So, how can we manipulate them? Let's kind of condense down as much as we can here and talk about a couple of things, and then we'll get more to the notation of this thing after we talk about how we can represent these things. So, let me get all my stuff in order here, sorry. Okay, so if I want to think about how can we manipulate vectors, this is the important thing to do mathematically speaking. So, manipulating vectors. Basically applying mathematical operations to vectors. How do you add vectors, multiply vectors, stuff of that nature. So I want to give you some rules for how this works and give you a sense of what it looks like. So, So manipulating vectors. I want to give you some rules for how we can multiply, add, and mathematically manipulate these vectors. So let's start with what it looks like if we want to do a vector times a scalar. So I'm doing multiplication, but I'm multiplying it by a scalar just to make it totally clear, so just a number. So if this is my vector, and I'll call this one, maybe this one is v instead of u. Doesn't matter the name, we'll typically just use lowercase letters for this. Well, if I wanted to see what 2v looks like, so if I wanted to multiply it by 2, what that will do is it will preserve the direction, but it will double the length. So this resulting vector would be like that, and we wouldn't draw this little middle piece with the arrow there. It would just be the same one, but that would be one of the original lengths and another one of the original lengths. So here would be the original magnitude v, and here would be another copy of that original magnitude of v. So it just doubles the length. Multiplying by 2 just doubles the length. Similarly, if I wanted to look at what does 1/2 of v look like, if this is our original v, trying to draw it as similarly as possible, all we would do is erase half of it. And again, so here's where the old one went out to. That was the old magnitude of v. Multiplying by 1/2 just shrunk it by a factor of 1/2. It's half as long as it used to be. One other thing, if I want to multiply by a negative sign, so what does negative v look like? Well, if the original v went this way, all that negative v does is switch the direction of the arrow. So instead of going that way, it's going to go that way. It just reverses the direction. So it's the same magnitude, still has the magnitude of v, but its direction has now been reversed. So that's what multiplying by a scalar does. Those are the types of the effects. So changes the magnitude, but not direction, other than kind of reversing the direction. So let me just say, changes the magnitude, but still parallel to the original direction. Okay, so that's what happens when you multiply a vector times a scalar. What if we want to add or subtract vectors? So let's talk about that. Addition of vectors, and for that matter, subtraction of vectors. But we'll treat subtraction as though we are adding a negative. That's how we'll do it. So same thing, let me give you two vectors. Let's say that this is our vector u, and v is similar to the vector that we had before. So there's v. I want to see what u plus v looks like. Well, the way that we do it when we do u plus v is we basically just tack them on end to end. So if this is the original u, copying that as closely as I can, and I move v over so that it touches the base of u. So here's u, here's v. This vector here, let me do it in red. This vector here, that's what u plus v looks like. So we get it by attaching them end to end. And you'll notice this ultimately is going to mean that addition is commutative, because if I did them in the order I just did them, where I did u first and then I did v onto the end of that, I could have done v first. V would have gone this way. I'll erase this in just a minute so it doesn't cover up everything. But so v would have gone this way to about there, and then I would have added u and it would have gone up this way, and we would have wound up with the same result. So I could have done v first and then u. and we would get the same result out of it. So the u plus v is kind of the diagonal of that parallelogram that we've created by sticking them end to end there. So just keep that in mind. Let me erase those last two just so they don't make it hard to read. And what if I wanted to do u minus v? Well, all I want to do is think of that as u plus negative v. And so again, we had u that goes this way. Just get that a little more clear. U went this way. Negative v is going to go back the same direction as v, but now it's going backwards. That's not quite the right direction. Maybe there. So here's the u vector going this way. Here's the negative v vector. And this is now the result. Starting point to end point. Can't draw a straight line for save my life right now. There we go. There is u minus v. That's what the vector looks like. So we could do u plus negative v. I also could have started similarly with the negative v first. So there's my negative v, and then I could have added u to it, which would have gotten me to the same point. So just like before, you can, when you actually tack them on end to end, I could do the u first, then the negative v, or I could do the negative v and then the u, and they both result in the same sort of diagonal of the parallelogram. It's basically the other diagonal of the parallelogram. If you look at this picture versus this picture, we have the same picture, the same shape. Again, going back to having this version of it. It's the same shape. The addition wound up being this long diagonal, the subtraction wound up being the short diagonal in this particular case. So you can see them, they just complete the sides of kind of these triangles here. So keep that in mind. The sum or difference of two vectors is going to be something that results in basically putting those two vectors together, vertex to vertex, so connecting them at some point like this, and then taking some sort of diagonal to complete the third side of the triangle. That's what we will see. So let me erase all these back out of here. Good. We'll just leave it like that so you can see it a little more clearly. So this is how, sort of geometrically speaking, we manipulate these vectors. And the important thing is that two vectors are equal. And I guess I should have mentioned this maybe even earlier, but this is maybe a good place otherwise. Two vectors are equal if they have the same direction and magnitude. And what this means is I don't care where these vectors exist in space. If I draw this vector right here, and I draw this vector over here, and I call this one u, and I call this one, it's meant to look the same as that one, v, well, they have the same direction and magnitude, so it turns out that u must be equal to v. And that's what allows me in these last few examples to just move these vectors around wherever is convenient to kind of touch them end to tail, starting point to terminal point, and move them around however we want. So this is the important idea. Two vectors are equal if they have the same direction and magnitude. So this particular u is u, but so is this u over here, and so is this u over here. They're all on different parts of the page, but they all have the same direction and magnitude. I can move them wherever is convenient. So that's going to be an important feature of these things. This is the idea that's just allowed me in these last couple of pieces to move these vectors around wherever it happens to be convenient. So keep that in mind. Okay. So I want to think about now a couple of other pieces. So some more different types of notation that we can do when it comes to vectors. So we've talked about a little bit, but I want to talk about more notation. So come on. Close enough. So more notation. There are more ways that we can write a vector. So I can write them with components, which I'll call component form. And the idea is, in practice, if I pick my vector over here again to be u, it's going to be made up of two pieces. Remember, we said it's two numbers. And I'm going to write them like this. I'm going to write u1, comma, u2. And I'm going to enclose them in these, instead of parentheses, in these basically spiky little sideways carrot-shaped things. So these little angled brackets are going to be how we think of this thing. And basically, this tells me, if I'm drawing it, how far should I draw this thing in the horizontal direction. So the first component is essentially what we think of as the x component. So this is going to be a lot like, let me just erase all of this. This is going to be a lot like the way that we write the location of a point. The first component tells us how far to go in the horizontal direction. The second component tells us how far to go in the vertical direction. And so if I were to draw my x and y coordinates and conveniently place u so that it sat right here, here's my vector u. If I break this down into two pieces, here's the horizontal distance I need to go, that's going to be u1, and then this is the vertical distance I need to go, this is u2. And in fact, this point, the terminal point right here, is the point using parentheses u1, comma, u2. So our vector u with the components u1 and u2 is the vector that points from the origin, from the point 0, 0, up to the point u1, u2. So if I look at that little directed line segment, that's my vector. But again, remember, we can move this thing anywhere in space. It doesn't have to be sitting right here at the origin. It could be at some other place. But the origin's an awfully convenient place to put it because it makes it very clear the endpoint is going to wind up at the point u1, u2 if I'm dealing with the vector u1, u2. So there's a close connection between the vector form where we write it in component form with these angle brackets and just using points in our Cartesian coordinates. But this same vector, so just to keep in mind, if I wrote it over here instead, if I started at this point and with the same direction and magnitude, this vector is also, even though it's not anchored at the origin, if I break it down into its vertical and horizontal components, this is also the vector u. So that should have been a vector. That is also a vector. This is also u1 and u2, and it's in a different location, but this point would be definitely not 0, 0, and this point would definitely not be u1, u2. But that's why it's convenient to put it at the origin if we want to. But the whole point is this difference, however, the difference in the x components from this point to this point is going to be a distance u1. The difference in the y components from this point to this point is going to be a distance u2. So another way we can represent vectors that's similar to this type of component form is we can represent vectors in terms of the following. So we can represent vectors in terms of I and j. And I'm going to write these with a little hat over them to distinguish them. And so I need to define what those two things are first. So this is going to require a little bit of extra background. So I've written these letters I and j, and I put little hats over them, and I'll call them I hat and j hat. And the first thing I need to do is define what it means for something to be a unit vector. So let's talk first about unit vectors, and then I'll introduce how we can use this notation. So unit vectors are vectors with a magnitude of 1. And I can create a unit vector out of an existing vector by just dividing it by its own magnitude. So if I have a vector that's too long and I divide it by 2, remember that'll scale it down by a factor of 1/2 and turn it from something that had a length of 2 into something with a length of 1. So this is the idea. If I want to deal with some unit vector, so I'll call it unit vector, in the direction of, let's say A. A is the vector I'm dealing with. Here's a vector A. It would be that same vector A just divided by its own magnitude. Right? So if I had a vector like this, here it is, and its magnitude, here's my A, it happens to have a magnitude of 3. Well, all I need to do is take A and divide it by 3, divide it by its magnitude, and I would get this vector right here, where that distance is now 1. It's pointing the same direction as the original vector A, but it's now scaled down so that it has a length of 1. And all we did was take the original vector and divide it by its own magnitude. In this case, I called that vector A, but again, we could have called it U, we could have called it V. The name of the vector, the letter we use for it, doesn't matter. So, I hat and j hat are two particularly important unit vectors. So, I hat is the vector, writing it in the notation that we used before, that looks like 1, 0. So it's basically a unit vector. You can tell it has a length of 1 by just using the distance formula on this thing. We'll talk about that down the line. In the direction of the x-axis. And j hat is going to be the vector 0, 1. So it is a unit vector in the direction of the y-axis. And if I treat these as my two forms, go back up to the example we were doing a minute ago. Oh man, let's undo that. There we go. Just wanted to zoom out a little bit so we can see both of these sections at once. Okay, so if I want to write this same vector up here that we were dealing with a minute ago, if I want to write u, which is the vector u1, u2, I could think of that as, using our rules of addition and multiplication that we had before, I could think of that as u1 times the vector 1, 0 plus u2 times the vector 0, 1. So again, these two numbers in here are just individual numbers. Each of these is a scalar. The vector is made up of this combination of two numbers. I've just broken them apart in a clever way so that if I were to distribute through, right, we would get, let me just do a quick notation here, distributing through, we would just get u1, 0 plus, distributing through on the other one, 0, u2. And when you add two vectors, we will add them component-wise. We will get u1, u2. So this is how we will add vectors. We'll do some examples of this in just a minute, and I'll make it totally explicit how we're going to deal with these things. So maybe we're putting the cart before the horse here, but I wanted to introduce all the notation first. But notice this line up here is just u1 times, what is this vector 1, 0? Well, that was how we were writing I hat. So this is u1 I hat plus u2 times this other vector, which is the same as j hat. So plus u2 j hat. So you may see this notation as well. And again, I'm going to use hats, these little squiggly sort of arrows, whenever I'm talking about a unit vector. So just again, as a quick side note, if A is a vector, then I would write, in my notation, A with a little hat above it is a unit vector that I would say is in the same direction as A. So that's just what I reserve this little caret shape over the tops of my vectors whenever I want to represent a unit vector, something with a magnitude of 1. Okay, so these are all the different kind of notations that we're going to have. Algebraically, we'll represent our vectors in one of these two ways, with these angle brackets and doing first horizontal direction, comma, vertical direction, how far you go horizontally, comma, how far you go vertically, or we'll use this I hat, J hat notation. Both are very common usages. I would say the I hat and J hat shows up a lot in physics books, so you'll see that a lot in physics books. And again, in a physics book, they would just write these as bold letters, I and J, as opposed to writing a little arrow or a little caret over the top of them. Okay. So now that we've got all the notations out of the way, let's talk about manipulating them. I just manipulated them right here, and we manipulate them in intuitive ways, but let me not just gloss over that. Let me go back and treat that idea a little bit more carefully. So again, we're manipulating things, but now I want to think about how do we manipulate them algebraically. Okay, so zoom in a little bit. Yeah, let's get it close to 100%. Okay. So, algebraic operations. Okay. If our two vectors are the following. So let's use u and v again. So if my vector u looks like u1, comma u2, and my vector v looks like v1, comma v2, then how do we add, subtract, multiply, divide, and so on and so forth? We just did it up there. It's going to be all very intuitive ways. So u plus v, when I add two vectors, algebraically, we add them component-wise. So we will get a vector. When I add two vectors, I get a vector, and it's just the sum of the two horizontal components. So I'll add the horizontal component of this plus the horizontal component of this to get the combined horizontal component of my new vector. And then I'll do the same thing for the vertical components. So I'll do u2, u2 plus v2. That's going to be the combined effect of how far I went up in this direction, how far I went up in this for this vector, and we combine them together. So this is what it looks like to add two vectors. If you wanted to subtract, you could think of it exactly as we did a minute ago, u plus negative v. It's just going to be u1 minus v1, comma u2 minus v2. And similarly, if I want to take a constant and multiply it by a vector, all you do is, if I'm taking c times my u1, u2, we can just distribute that c through, and it becomes cu1, comma cu2. So all I have here is c times u, here's c times u written out explicitly in terms of its components, and we can distribute the c through to those two terms as we've done here. So we utilized all of these operations just a minute ago. Hopefully it wasn't too scary, but this is the more formal way, just writing it down to make it totally clear. These operations yield to a bunch of semi-intuitive properties. And so let's look at the properties of vectors. First one I want to mention is the commutative one. We drew that with illustrations earlier, but basically if I take u plus v, that's the same thing as v plus u. They give me the same result. We have an associative property. If I do u plus v plus w, and I do the v plus w first, well, that's the same as doing the u plus v first, and then adding w to that. So there's like an associative property. We're going to define a zero vector. So I'm going to do u plus a 0 vector, which is just going to be a 0 with the little arrow over it. And when you add 0 to something, you get 0. And so as an important note here, this 0 vector is just 0, comma 0 is the 0 vector. And this gives us basically an additive identity. You can add 0 to a number and get it back. You can also add a 0 vector to a vector and get that same vector back. Similarly, if I add the positive version of a vector to the negative version of that same vector, you will get 0, but not just 0, you will get the 0 vector. What else do we got here? If I'm interested in figuring out what's the magnitude of c times u. So I've got a vector u multiplied by a constant c. What is the magnitude of that combined larger vector? Well, it's just going to be the absolute value of c times the magnitude of the vector u. So we can split it up that way. Lots of other things. So these first ones here, these all had to do with basically addition rules. This has to do with sort of the length. I want to go over some that have to do with multiplication. So for example, there's a distributive property. If I am multiplying a sum of two vectors, so I've got a sum of two vectors here, and I'm multiplying it by a constant c, a scalar, that constant distributes through, and we'll get cu plus cv. There's also a distributive property where I could add my two scalars and multiply by u, and it distributes through similarly, cu plus du. So there's multiple distributive properties. We also have an associative property of multiplication. So if I do c times d times u, I can think of it as being c times d first and multiplying that scalar by u. I could do c times the vector that's the result of du, and I can switch the order, commutativity of the two scalars, to be d times cu. All of those are equivalent. Sort of the order of the multiplication by the scalar doesn't matter. And just like we had a 0 vector, we have some properties that have to do with 0 scalar. Oops, let me do what I'm talking about. 0 scalar. So what happens if I take the 0 scalar and I multiply it by a vector u? So what I'm doing is I'm taking each component, as we've seen up in our the rules of how we did our multiplication. I'm taking each component of u, u1 and u2, the horizontal and vertical components, and I'm multiplying them both by 0. And the result of that is you get the 0 vector. All those individual components turn to 0. Similarly, any constant times the 0 vector will give me the 0 vector. And what happens if I multiply a vector by the scalar 1? Well, that has no effect. So all of these properties, these all have to do with multiplication. So here's a big long list of a bunch of properties. And in just a minute we'll do some examples to start to get comfortable with these. I just wanted to kind of get all of the big picture ideas out of the way first. So let's do a few examples while we're at it. So let me kind of zoom this out, do a couple of quick examples. So these should all be fairly straightforward, fairly easy examples. Okay, first things first. Let's say that I have a vector u that's equal to the vector, I don't know, 2, negative 1, and I have some constant that's equal to, I don't know, 3. What is, and while we're at it, let's do a couple of other things. So I'm going to have a vector u that looks like that. I'm going to have a vector v that looks like, I don't know, 4, 0, and that constant that's going to be 3. So let's look at a couple of things. What is, first and foremost, c times u? Well, c times u will just be 3, that's what c is, times the vector u, which was 2, negative 1. And according to our rule of multiplication by a scalar, you can just distribute that 3, 2, and we'll get a vector out of it that is going to be the 3 times 2, comma 3 times negative 1. And we get 6, negative 3. So there's the result of multiplying by that scalar. Similarly, what is u plus v? Well, we said that's just going to be the vector u, which is 2, negative 1, plus the vector v, which is 4, comma 0. And when we add those two things together, we will just add component-wise. So add the first components together, 2 plus 4, and then add the second components together, negative 1 plus 0. And what's the result? Well, that first number adds to 6, the second number adds to negative 1. So that's what it will look like if you just add a couple of vectors together, or multiply a vector by a constant. That's how we do it with actual numbers. We do a couple more examples. I want to find the vector with initial point of, let's say, 1, 3. So there's the coordinate of where this vector starts, and the terminal point of 4, 2. So if I draw this real quickly, here's my x-axis and my y-axis. I'm saying that we're starting at the point 1, 3. So I'll say this is 1 and this is 1, 2, 3. So 1, 2, and 3 up. We'll do some more in this direction as well. So it starts at the point 1, 3. So here's the point 1, 3. There's its initial point. And it stops at the terminal point 4, 2. So oops. Here's the point 4 and a height of 2. So it stops right there at that point. So this is the vector I'm talking about. It goes from there to there. I want to find that vector. Well, when you draw the picture, it's pretty obvious. How far are my two components? So basically, I want to break this vector down. So let's call this vector, whatever, v. V is going to have two components. I want to figure out what they are. So I want this number and this number. The first number needs to correspond to the horizontal distance. Let's do it in color. I need that distance. How far did this thing travel horizontally? Well, you can see it started at an x-coordinate of 1. It wound up at an x-coordinate of 4. If I take the difference and do 4 minus 1, we get that length, 3. And so that's what this number needs to be, 3. Similarly, for the second component, it's the vertical distance. So I'm looking for, well, I'll just sneak it out over here. I'm looking for that distance. And in this case, it started at a height of 3. It wound up at a height of 2. We do the 2 minus the 3, and we get negative 1. It went down. Oops. Negative 1. So essentially, all you need to do to figure these two pieces out, these two components, it's the terminal point minus the initial point. So terminal minus initial. If I do 4, 2 minus 1, 3, I'll get 4 minus 1 for the first component, which is the 3, and I'll get 2 minus 3 for the second component, which is the negative 1. If you just draw the picture, you don't even need to keep any sort of formula like this in mind. And so that's often what I'll do, is if I have a terrible memory, just draw the picture and you can figure these things out easily enough. Okay, so if I give you that this vector has the following, let me try one more. So if our vector u that we're interested in is the vector 2, 3, and if it has an initial point of -1, 1 is where it starts. What is its terminal point? So again, if I draw the picture, this is an easy problem. I'm saying that it's starting at the point -1, 1, so it's starting at this point right here, -1, 1. Here's my x and my y coordinates, and it's going over 2 and up 3 from there, so it needs to go over 2, 1, 2, and then up 3, so up 1, 2, 3. And I've drawn it in a terrible place where I can barely see it. So basically, it's going to go up to a height of 2, 3, and that one snuck in there is going to be 4. I should have drawn this whole thing. In fact, let me do that. Let me see if I can move this whole piece. Let me see if I can slide it down here. Okay, yeah, give myself some more room. Perfect. Okay. Let me just erase the top of this a little bit. Give myself some more room. So there's the y-axis and a distance of 4. There's the point that we wind up at. So this is what the vector looks like. Again, we've gone over and then up. This distance in the horizontal, this distance in the vertical, so 3 in this direction, 2 in this direction. And what is the location of this new point? It's at +1, 4. And how do we get that without the picture? All we need to do is basically treat that point -1, 1 as a vector and add u to it. So basically do -1, 1 plus 2, 3. Right, here's the initial point, and here's u, and I'm adding them. And we get, what is -1 plus 2? That is +1. And what is 1 plus 3? That is 4. And that gives us our vector that points to the terminal point. We just need to convert it from, so drop the vector symbol and convert it to a single point. Think of it as basically adding and subtracting a bunch of vectors. So this is the idea, again, kind of how we can manipulate some of these things. Another concept that's going to be important, and then we'll do some more complicated examples, is this idea of magnitude. We've used this word, we've said that it's basically the length. I just want to make it totally clear. If my vector u is u1, u2, how do I find the magnitude of the vector? So this implies that the magnitude, which we said is this symbol, or maybe you'll see it with single lines, but it's just going to be, we're writing a vector like this, and we're breaking it up into these two components, u1, u2 on this side. This is a right angle, and here's our distance that I'm hoping to find over here, that is the magnitude of u. How do you find the length of that hypotenuse? Well, it's just Pythagorean theorem. And it's basically just the distance formula. So it's going to be the square root of u1 squared plus u2 squared. We get that magnitude. So that's how we can find this magnitude that we keep talking about. So again, very quickly, how do I find the magnitude of if u is equal to the vector, I don't know, 5, 2? What is the magnitude of u? Well, the magnitude of u is just going to be the square root of the sum of the squares. So 5 squared plus 2 squared. 5 squared is 25, 2 squared is 4, so I just need to add those two numbers together and take the square root. Turns out it is root 29. There's our magnitude. So nothing scary with that. Okay. So now that we've got all of these concepts out of the way, why are we talking about this in a trig class? So how is any of this connected to trig? Well, we'll see a little bit more of this in the next section, which incidentally is our last section. 7.5 will be our final section, our last video, at least the last video for new material. So let's think about this. We can represent, what we've seen is basically we can represent these vectors in a very similar way to the way that we represent a point. So if I've got my vector u right here, and that vector has components u1 and u2, then this point, the terminal point, if I put the origin, or the initial point at the origin, and I put the terminal point up here, then vector u matches the terminal point, right? The coordinates of the terminal point, if the initial point is 0, 0, the coordinates of the terminal point are the same as the two components of u, u1 and u2, u1 and u2. We've already learned how to represent a single point like this in terms of polar coordinates. It turns out we can also represent the vector in the same way. So how could I represent this vector? I could represent it in terms of, instead of those two components, I could think of the direction as an angle theta. And I could think of the length here as being, so the length of this side as just being the magnitude of u. And so we can use those two things to determine and represent our angle. So basically what I'm suggesting is, in terms of all of these, using that angle that I've got written right there, I could also represent this same thing as the following. What is this component if I don't actually have u1, but instead have theta and I know the magnitude of u? Well, it turns out this is equivalent to the magnitude of u, whatever that distance is. You can think of it as r, times the cosine of theta, and the magnitude of u times the sine of theta will give me the y component. So it's the same connection that we've seen. X coordinate goes with cosine, y coordinate goes with sine, and the magnitude, what normally we treated as r, this distance, we're now just calling the magnitude of u. So this is basically from polar coordinates. It's just polar coordinates with magnitude of u in place of r. So that's the idea. We're going to be able to talk about vectors and the components of vectors in terms of sine and cosine, and this will be useful down the line. We'll see some examples in just a minute where we use that angle. Okay. So what kind of stuff can we do? We've done some easy examples, but what can we do with vectors? How are they useful? Well, I've already mentioned some of the things they can represent way back at the beginning. Velocity, acceleration, force. We're going to be able to do all of those same types of things basically in very sort of, we're going to be able to do physics. That's what I'm trying to get at. We're going to be able to do physics type problems using vectors. And so let me do a bunch of examples. These are types of things that you might wind up seeing on the homework, sort of more complicated, difficult problems. So the first thing I want to do is find the resulting force of adding up a bunch of different forces. And oftentimes this is called the resultant. Not just in the context of forces, but when you add up a bunch of vectors, you call the result the resultant vector. Okay. So here is the picture, and what we can call this force F for force with a little arrow over it. So we're talking about a force vector. So let me draw you a picture. Let's say here are my axes, X and Y, and here's a bunch of forces that are acting on this. So maybe one goes off in this direction, and that is 20 degrees. And maybe this force, in fact, let me draw them all first. Maybe I've got another one that comes up this direction, right there. I'm going to call this one V1, this one V2, and then maybe I've got another one coming back this direction. I'll call that, maybe that's a 45-degree angle. Maybe that right there is a 36-degree angle. And the magnitudes are as follows. So this first one has a magnitude of maybe 5 pounds of force. So here's one thing that you should know. One of the first things you'll learn in physics. There's actually kind of two different meanings of the word pounds. There's a pound mass and a pound force. The reality is, when we talk about pounds, we aren't measuring a mass, we're measuring a force, and it's the amount of, so if I tell you that I weigh, whatever, 160 pounds, I'm telling you that that is the amount of force that my body applies to the ground, essentially, due to the acceleration of gravity here on the surface of Earth, acting with how much stuff I'm made up of. The actual units of mass in our weird American system are actually called slugs. So if you ever hear the term slug, a slug is a unit of mass, pound is a unit of force, but nobody ever talks about slugs, so we often think about pounds as a mass, where we just assume that we're talking about here on the surface of Earth, where gravity is kind of built in. So really, when I talk about pounds in physics, it's always going to be a measure of force, how much force is being applied. And it may be worth mentioning, oh, this vector over here, by the way, is V3, and let's say that it has a magnitude of 7 pounds of force acting in that direction. Okay, just as a quick side note, because this comes up in physics a lot, and it's going to come up in all of these problems, Newton's second law is one of the foundations of physics, and it basically just says that force is equal to mass times acceleration. So force equals a mass times an acceleration. And here on the surface of Earth, we assume that the acceleration that we're talking about due to gravity is just constant. It's 9.8 meters per second squared, or about 32 feet per second squared. And so even though we measure our force in pounds as being kind of the amount of force that our body applies to the ground if we're talking about our weight, this is the thing that would be slugs, and we multiply our slugs by that acceleration and it would give us the units of pounds. So this would be pounds, this would be super weird units of slugs, and acceleration, this is going to be in units of, in what we're doing here, feet per second squared. So there's all the units. That's not stuff that you need to know, but I just want to talk about why we're using measurement of pounds here. We think of pounds as being like a mass. The reality is pounds are units of force. Okay, so here's our picture. I just want to figure out the combined force of these three forces. Imagine they're playing tug of war on some objects sitting here at the origin. Basically, what is the net result of all of these forces? So, I want to add up all of these forces. The resulting force F is just going to be the sum of V1 plus V2 plus V3. I need to add up the three forces. But I need to have them written in component form. And I don't have them written in component forms. I know the direction they're pulling, and I know the magnitude of that. And so I need to convert every single one of those into component form using this formula that we just used right up here. So that's the formula I need to use. So let's look at all of these forces. Let's start with V1. Here's what V1 looks like. So V1 is going to be written component-wise. The magnitude of the force is 5, and it's pulling in a direction. What I've written right here is 36 degrees. If we want to use the reference angle from the positive x-axis, I would need to figure out this angle right here. We can do that. Or I can just think of it as a right triangle and try to break it down into these two separate components where I know this angle, and I could think about opposites and adjacents in this right triangle. So basically, we have to pick, do I want to use this blue right triangle or do I want to use this red right triangle for that particular shape? The red one, we don't know the angle. Obviously, it's 90 minus 36 degrees. The blue one, we do have the angle, but it's not the traditional one where that angle is measured from the positive x-axis. So we get our choice. I'm going to do it the weird way. I'm going to treat it like this is the triangle that I'm looking at. So I want to find, this is my y coordinate, this is my x coordinate, this is what's 36 degrees, and this length on this side is the 5 pounds. So that's the triangle I'm looking at. It's the blue one. I guess I should have drawn it in blue. Here's the triangle that we're looking at right now. Okay. So relative to the angle as we've drawn it, the x-coordinate is actually opposite over hypotenuse. So if I do the opposite over hypotenuse, that is sine. So the sine of 36 degrees is equal to opposite over hypotenuse, which tells me that x is equal to 5 times the sine of 36 degrees. Alternatively, if we'd used the red triangle instead, and we would have wound up with what, 54 degrees, and it would be 5 cosine of 54 degrees. It turns out the cosine of 54 degrees is the same as the sine of 36 degrees. So, if we had done this with the red triangle. To find y, I will do the cosine of 36 degrees, which gives me the adjacent over the hypotenuse. So we're just doing our SOHCAHTOA here. We get that y is equal to 5 times the cosine of 36 degrees. And again, these have units of pounds when it's all said and done. So there's my two components. The x component we just saw was 5 times the sine of 36 degrees. The y component is 5 times the cosine of 36 degrees. And again, units of pounds. For V2, this one we luck out because the angle for our V2 is measured from the positive x-axis. It's 20 degrees. And so this one's straightforward. It's just going to be the magnitude, which is 10. The x-coordinate is the cosine, so cosine of 20 degrees. And the y-coordinate is the sine of the 20 degrees. And that's also in terms of pounds. And so just to make it clear, basically what I'm saying is this was the triangle we were doing in that case, where that is 20 degrees, and this is a magnitude of 10. This is x, this is y, and this is our right angle. That is, whatever, let's make it green. That one is the same as that one right there. I guess I don't need the right angle. Clear enough. Okay, So that's how we got V2. How do we get V3? Let's pick a new color. Let's do this one in orange. So I'm going to do this triangle. Doesn't really matter. I guess maybe it's better. Let's just do this triangle, the one where the angle is already written inside. Let's do that one. So that's the triangle I'm dealing with for this one. I can draw it right here. There's my 45 degrees. Here's the x coordinate I want, here's the y coordinate, and this distance is 7. And again, that is the, keep drawing it in the wrong color here, there's the orange triangle. So doing the same thing, relative to the angle that's given, x is opposite. So in this case, we will have sine of 45 degrees is equal to opposite over the hypotenuse, so x over 7, and cosine of 45 degrees will give me the y over 7, and we will result over here solving for x and y respectively with 7 times the sine of 45 degrees and 7 times the cosine of 45 degrees. And all we need to keep track of, though, and keep in mind is in our picture, I found these lengths, but I didn't find the correct signs of the lengths. We're in the third quadrant. These two things really represent both a direction and a magnitude. All I've found is the magnitude. So these both go in what are considered the negative directions. So I need to toss in negative signs in front of both of those terms there. So that's what I do. All I do now is basically plug all of these into a calculator and then add them up. So plug them into a calculator and add. And what we'll get, if I didn't screw this up when I did this a minute ago, for my first one I got about, so I'm talking about V1 right now, I got about 2.94-ish, comma 4.05. The second one I got about 9.40 and then 3.42. And for the last one I got negative 4.95, comma negative 4.95. And I add them all together, so these are, again, just approximate. I add them all up, and I wound up with a resulting force of 7.39 in the x direction, 2.52 in the y direction. And again, this has units of pounds on it. So again, just to make it clear, what colors did I use? This is the blue one. Here's its numbers. Orange one, and the last color I needed was green. Green one, and green one. Okay. So there's the resulting force. We just added them all up. The hard part was converting to component form given an angle and a magnitude. So there's one example of something that you'll encounter on your homework. What else? Let's do one or two more examples. I know these are taking forever, but rather do too many than too few. Okay, so let's do another example. Here's a tricky one. Imagine that I've got some solid sort of ceiling here. I'm drawing a little diagram, and we have a weight hanging from it that's anchored at 2 points. So one is anchored down like this, the other one is anchored over like this, and we have this mass hanging down. So hypothetically, let me insert the straight line that would continue. I've got a mass that weighs, I don't know, 50 pounds hanging down. maybe this angle is 60 degrees, and this angle here is 30 degrees. And I want to find basically these two different forces. So I'm going to call this one T1 and this one T2. And I'm using T because they're really, you can think of them as tensions. So our goal is to find the tension on the two ropes. And tension is really, again, just a matter of force. To do this, it's similar to the problem that we just did. You can think of these as having sort of vectors associated with them. So T1 is, I'm going to draw it in blue. There's a force vector pulling that way. T2 is a force vector pulling this way, and the mass itself is a vector pulling this way, straight down. And in this case, they're all playing tug-of-war, and who's winning? Nobody's winning. The idea is, in this case, the mass, if it's hanging there, it's not moving. If the mass isn't moving, and we're assuming that it's not, we wind up with what's called a statics problem. If you wind up going into engineering, you will take an entire class in statics. If the mass isn't moving, the forces must all be in balance. This is hopefully semi-intuitive idea, even if you're not totally comfortable with forces. So they must all be in balance. Meaning the net force, the combined force of all of them must be 0. So all of those things have to add up to 0. So I'm going to write them in the following way. Let's think of our three forces that we're going to add up. We're going to take T1, which is, let's call it A1 and A2 for its first and second components. We'll have T2, and we'll use the letter B for it, so B1 and B2 are its two components. And then we have this downward force, which I guess I should give a letter. Maybe we'll call this capital F, pointing down. Capital F is the one pointing down, and in component form, we actually know what this is. What is the horizontal component of force acting on this? Well, it's pointing straight down, so there's 0 horizontal force. And how much is in the vertical direction? Well, it's all 50 pounds, and it's with a negative sign because it's pointing down. So there is what our force F looks like, pointing straight down. And we know, according to the logic that we just went through up here, if I add up all of these forces, T1 plus T2 plus this F, I should get the 0 vector. Let me put that 0 vector over that as well. They add up to nothing. It's not moving. So this is the idea. This is our picture in this case. So I'm going to use those angles and figure out what else I can determine so that I can ultimately find these A's and these B's. I've got to find all 4 of those pieces of information. So let's look a little more carefully at, say, T1. So if I look at T1, it's going in, see if I can draw a straight line. It's going in close enough, that direction. Let's draw it with its components. We know that this angle up here was 60 degrees, so what does that mean this interior angle is? It's 30 degrees. This one's 90 degrees, and that means this angle here must be 60 degrees. So that's our 30, 60, 90 triangle. And the magnitude is the thing that I don't really know. So it has some magnitude of what we'll just call the magnitude of T1. That's the length of that remaining side. So I can write this in terms, so I can write that our vector T1 is in terms of those components. It's whatever its own magnitude is, T1. So the magnitude of T1 times the cosine of 60 degrees, comma, the magnitude of t1 times the sine of that same 60 degrees in this case. So again, all I'm doing is using the thing that we used earlier, where if you know the angle, you can break down the components of a vector into basically the magnitude of the vector times the cosine of the angle, magnitude of the vector times the sine of the angle for the x and y components separately. So this formula is the same as, zoom way back here, it's the same thing that we did for these essentially, but really it comes from this formula right here. This is what I'm using. I can break down a vector into its two component forms as long as I know the magnitude of the vector and I know the angle. I can write it like this. And so that's what we're going to do here. All we just need to keep in mind is, zooming back in, we're almost done here, which direction does each of these point? Because this angle 60 degrees that I used isn't measured from the positive x-axis. Normally we would think of this being the positive x-axis. I didn't measure that angle. Really this angle would be 120 degrees. We could do that way if we preferred. But I just basically need to keep track of what are the signs of these. Well, the y component is clearly pointing upward, so it's going to be positive. But what about the x component? Well, it's pulling to the left. And because it's pulling to the left, that component of the force is going to be negative. So I'm going to write it like that. If we just used the 120 degrees instead, we wouldn't have to worry about this, about the signs. It would have just worked out. But I don't want to think about that piece and make anybody too much more confused. So there's that picture. And now let's do the same thing for the other one. The other vector is pointing this way, whereas we've split it up. This angle was supposed to be 30 degrees. That's a right angle, and that means this one must be 60 degrees, and this has a magnitude of, I guess I can do my double lines, because that's what I've been using in everything else. Let me go back and make this consistent, sorry. This has a magnitude of whatever the magnitude of T2 happens to be. So again, and here was the ceiling up there, here's the ceiling right here. That's our reference point. Okay, so same thing. What are the components of this vector T2? Well, it's just going to be the magnitude of T2 times the cosine of, in this case, the angle is 30 degrees and it is measured from the positive x-axis, so I don't even need to worry about sines. It's just cosine of 30 degrees. And the other one will be the sine of 30 degrees. So magnitude of T2 times the sine of 30 degrees. And this one's nice because I know the cosine and sine of 30 degrees and of 60 degrees. So we can replace these all with actual numbers. Going back up to this one, what is the cosine of 60 degrees? Well, that's a half. So this is just going to be negative 1/2 times whatever that magnitude is. I'm just evaluating the cosine of 60 degrees. That's all I'm doing. And same thing here. What is the sine of 60 degrees? That's √3/2. So there's what that vector looks like. Doing the same thing down here with this vector. What is the cosine of 30 degrees? That's √3/2 times the magnitude of T2. And this other one, sine of 30 degrees, that's a half. So half times the magnitude of T2. Okay, so there's all the different pieces. We eventually have broken it down so that there's two unknowns. There's this, whatever this magnitude of T1 is, it shows up in those two places, and whatever this magnitude of T2 is, it shows up in two places. We have two unknowns to solve for. That means we're going to need two equations. And I can get those equations, so we need two equations for our two unknowns. We can do that by looking at the horizontal and vertical components of our force balance separately. So if I come back here, get the whole thing in the picture. here's our force balance. We just said if we add up all these forces, we get 0. It looks like one equation, but it's really two equations, because when we're dealing with vectors, the sum of all of the x coordinates will have to be 0, and separately the sum of all the y coordinates will have to be 0. So if I look at all the x coordinates, that's what we're doing in the horizontal one. I'm just going to take all these components, t1, t2, and f, and add up all their x components and know that I need to get 0 because it's not moving in the horizontal direction. Then I will add up all the vertical components and I know that I need to get 0 because it's not moving in the vertical direction. If it's not moving, it means the net force acting on it must be 0. All the forces are in balance. So let's do that. Here are all of the horizontal components. I'm going to add the horizontal component of t1, which is -1/2 times the magnitude of t1. Then I'm going to add to that the horizontal component of t2, which is √3/2 times the magnitude of t2. And the horizontal component of f, you'll remember it was pointing straight down, so it was 0. It had no horizontal component, and all of those need to add up to 0. For the vertical components, I will do all the y coordinates. So the y coordinate of t1 was √3/2 times the magnitude of t1. The y component of t2 is sitting right here. It's 1/2 of the absolute value of, or the magnitude of t2. And the vertical component of f, if this was our f pointing straight down, remember it was 0, -50, so it is -50, and that has to be equal to 0. So there's my two equations for my two unknowns. All I need to do is solve them. It just looks scarier than it is because we're carrying around this giant chunk. You could just think of this as being like, I don't know, you could just give them letters. Here's A, here's B, or something like that, or and maybe it would look less scary if you weren't carrying around all these symbols. But at the end of the day, I can solve this first one for one of them in terms of the other. So basically for this first one, let me add this term to both sides so that I can get it onto one side. So I'll have 1/2 times the t1 term is equal to √3/2 times the t2 term. I can double both sides, and that'll cancel the 2's in the denominator, and we will have solved and found that the magnitude of t1 is equal to √3 times the magnitude of whatever the t2 is. And let me erase this part up here because it's getting in the way. Down here, I can now use this piece and plug it in right there. So I'm going to substitute that in. So in this case, I'm going to get √3/2 times t1, but I already found that t1 is √3 times t2. So all I've done is basically that piece in parentheses right there just came from up here, came from this relationship. I swapped out the t1 term. Plus 1/2 of t2 minus 50 has to be equal to 0. And so I can move that 50 to the other side and combine these two terms into one. This √3 times √3 will be 3, so I will have 3/2 of the absolute value of t2 plus 1/2 of the absolute value of t2. By absolute value, I mean magnitude. I know I've said that word. I use them interchangeably. It's kind of the same idea. This is, in a sense, a generalization of the idea of an absolute value. Absolute value just tells you how far a number is from the origin. Forget whether it's to the left or to the right on your number line. It's just how far away is it. And so this has the same effect. Absolute value is kind of the magnitude of a number, so to speak. Okay, these two things add up to, if I got 3/2 of this thing plus another half of it, I've got 2 of them total. So I've got 2 of these things equal to 50. So what is one of these things? Well, one of these things must be 25 pounds. And if T2 is 25 pounds, then I can take this result, go back to this relationship over here, and see that T1 is going to be 25 times root 3 pounds. And we've now found essentially the two tensions that we were looking for. I can go back and figure out those exact components of the vectors, but those are the two tensions. In fact, let me just say, change so that I don't have to do any more. Yeah, that's good. That's what I was looking for. I was trying to find those two tensions. And that's exactly what they are. So here are my two answers, the amounts of tension on those two pieces. So here's the problem all at once. That's what we had to do, break it down into all of those pieces. I've got one more example. Is it worth doing? This video is already so long. Why not? We'll do one last example. Bear with me if you want. I don't blame you if you need to take a break. I wish I was taking a break. But let's do one more. So let me do one last example. Kind of zoomed in here. Okay. This is a word problem. So a ferry, like a boat, needs to cross a river. So basically, to a dock directly east of our starting point. The ferry can travel 12 miles per hour in still water. So if it was just on a pond or a lake where the water wasn't moving, it could go 12 miles per hour. The current of the river moves due south at, let's say, 4 miles per hour. What bearing should the ferry take? So basically, what direction does the ferry need to aim to cross the river? Okay, so basically, let me just put in our little compass here. We have our north, east, south, and west. And we've got a picture that looks like this. We've got a river that's flowing due south. And the ferry's starting at this point, and we want it to wind up going straight across to this point. So that's where the ferry's going. This is going 4 miles per hour. To account for the fact that there's this sort of southward drift, the ferry can't aim due east to go across. It's going to have to counteract that by going this direction. Right? So that's sort of the direction the ferry should go, where this component needs to be 4 miles per hour. So let me draw this a little more clearly. Let me erase that. Come on, eraser. There we go. Let me just put this with a question mark there. This is where the bearing of the ferry that we're trying to find. Okay, so I want to think about this picture, basically. We've got a picture where I want to know what this angle is. And I know that to counteract the force of the river going 4 miles per hour south, I need my ferry to go 4 miles per hour in that direction, north, to counteract it. So it'll have a component that's going to fight the river, and we'll have a component that's going in the direction that it wants to go. And we need the component that fights the river to exactly balance out. We also know that it's capable of going 12 miles per hour in whatever this direction is that it winds up going. So this is what I want to figure out, is basically what is that angle theta? What direction should this thing be going? Hopefully these numbers are clear. So we can find the component form of this, so maybe we call it the velocity. Maybe that's what we should do. Here's the true velocity of kind of what the fairy's trying to do. And we know that's the magnitude of its velocity is 12. That's how fast it can go. So I want to find this other component right here. What is the horizontal component? Well, this one's easy because this is just from Pythagorean theorem. I can figure out that piece. So that piece, the horizontal component, is just going to be whatever, so we'll just call it x, because it is going horizontal. I know that x squared plus 4 squared must be equal to 12 squared from the Pythagorean theorem. And so if we solve for x, we'll get x squared is equal to, this is 144 over here, and I need to subtract off 16. That's where that piece goes. So I'm kind of doing a couple steps at once. That's 128. So let me write that there, 128. And that means that x is just going to be the square root of 128. And I don't really care about the fact that that's divisible by 4. We could definitely simplify this thing. Not worried about that. So I know that the vector v is square root of 128 comma 4. And that is sort of the bearing that this thing has to take. This is in the easterly direction, and this is in the northerly direction, if you want to think about it like that. So, but what we really want is, what is the angle? Well, to find the angle, we didn't actually need to find this number necessarily. We could have done it with the remaining two other sides. So for example, if I wanted to not use the square root of 128 that I just found, I would be looking for a relationship that relates the angle to the 4 miles per hour and the 12 miles per hour, the opposite and the hypotenuse. And that is going to be sine. So the sine of this theta is equal to 4 over 12. Which simplifies, hopefully, obviously, to a third. And so that tells me that theta is going to just be, I'll just apply the inverse sine to both sides. It's the angle whose sine is a third. So there is what that number looks like. We could plug that into the calculator, and we would get in radians, this is about 0.3398 radians, but that's not terribly useful. If we're talking about this in real life, what bearings are typically measured in degrees. So if I wanted to convert it to degrees, it turns out this is about 19.47 degrees, and the bearing is north of due east. So north of east, because that is the angle we are trying to go north of east. 19 degrees north of due east. There's what the answer to that one would look like. So hopefully all these application problems, I think I've covered most of the difficult ones. You'll see some similar ones on the homework. Give them a shot. I think hopefully we've tackled everything that you'll need. So I'll have the last video for section 7.5 up probably early part of next week. So see it soon.